a sustainable blue economy with thermodynamic geoengineering to power Biorock technologies. The small island developing states or SIDS rebranded themselves a few years ago as the large ocean developing states on the basis of the 30% of the global economic exclusion zones or EEZs they control, but the tiny nation Tuvalu, with a territorial land mass of 25.1 square kilometers, has an exclusive economic zone of 753,139 square kilometers. An economic multiplier of 30,000 when this surface area is utilized to produce energy with ocean thermal energy conversion. And the 39 SIDS and 18 associate members of United Nations regional commissions that face unique social, economic and environmental vulnerabilities have similar potential with the same technology. But not all ocean thermal energy conversion is created equally. Typically, with conventional OTEC, water is brought to the surface by massive pipes to condense a working fluid after it has passed through a turbine to produce power after the working fluid was first vaporized using surface heat. The thermodynamic efficiency of this process is only about 3%, and the 97% of the surface heat diluted by the cold water is dispersed outward towards the poles that in the case of the Arctic is warmed 4 degrees over the course of 1,000 years at the same time as the tropics are cooled by the same amount. Instead of using an upwelling strategy, thermodynamic geoengineering doesn't allow water to move between the thermal layers of the ocean. It instead uses the phase changes of a working fluid to move heat from the surface to a depth of 1,000 meters, which provides 226 years of global warming respite. It also mitigates the two greatest threat to island nations, sea level rise and storm surge. This is because the coefficient of expansion of sea water is half at 1,000 meters it is at the surface, and heat moved into deep water isn't available to melt polar and Himalayan ice caps, and surface heat moved into deep water can't power cyclones. Using phase changes of a working fluid, instead of with the sensible heat of water, heat is moved 2.5 times more efficiently with thermodynamic geoengineering than with conventional OTEC, and accordingly thermodynamic geoengineering can produce 2.5 times more energy as well. At scale, thermodynamic geoengineering can produce over twice as much energy as is currently being derived from fossil fuels. From a depth of 1,000 meters, heat diffuses back to the surface at a rate of 1 centimeter a day to the bottom of the mixed layer, and 1 meter per day through that layer. So, it is back at the surface in about 226 years, where it can be recycled to produce more work. Over the course of 13 cycles, all the heat of warming can be converted to work, and the waste heat of those conversions can be dissipated back to space, thus eliminating the problem of global warming. An amalgam of the SIDS economic exclusion zones with the economic and technical might of the Asia-Pacific region are a recipe for a vibrant and prosperous sustainable blue economy that can thrive on the cheapest energy that can be had with thermodynamic geoengineering.